if you are calculating statistical significance, the whole underlying forces are just these three, and that's effect size, standard deviation, and sample size. This relationship governs the entire statistical significance. If this ratio goes up, your statistical significance increases. If this ratio goes down, your statistical significance decreases.
Looking like a baddie, I show up and make them stop. Wanna know my name so badly, cause I run this whole block. Flip my hair, move my head, show the world I'm royalty. When I walk by, they be taking bows, cause they know I'm the queen, yeah.
Hello everyone, this is Ishan Goel from VWO. I'm working as the Associate Director of Data Science. I'm very excited to speak for experimentation this year. Today, my talk is centered around statistical significance. I've been researching in statistical significance with my team for the past 3 years. And what I've realized about statistics is that it is quite indispensable for experimentation. It is because the world that we live in is random, and hence most metrics that we record are also random. And hence, experimentation cannot proceed without statistics. In today's talk, I'll be introducing the basic framework of statistics that powers all experimentation, be it Bayesian, be it frequentist. I'll be exploring the different kinds of errors. I'll be exploring the how do you determine the appropriate sample size for an experiment, and I'll also be finally exploring the Bayesian and frequentist debate. So, very excited to speak on the topic. Let's get started. And here we go. So, I would like to start with a very, very interesting topic of how did experimentation that you are today doing in the form of A/B testing, how was it invented and how it came about? So, this is quite an interesting story. So, what we do in modern A/B testing is nothing but randomized control trials. The statistical name of the methodology is randomized control trials, and it is a story from 1920s. So, R.A. Fisher, the father of modern statistics, he was a biostatistician, and what he wanted to do one day was that he was running an experiment, you can say. He wanted to test out whether a new fertilizer that he has made does it practically increase the yield of his crops or not. So what Fisher did was he neatly divided his field into two halves and then sprayed the fertilizer on one half and did not spray the fertilizer on the other half. After, as the plants grew and the yield was collected, Fisher realized the error that he was making and why the results of the study might not be trustworthy. So he realized that different parts of the field were getting different sunlight, different amount of sunlight. There was difference in soil quality as well, and different amount of water was probably seeping into the different parts of the field because of the different elevation of his field. Essentially, all these variables were essentially uncontrollable by Fisher. He could not create an apples to apples comparison, and these variables in statistics, they are called confounders. So what Fisher did was a very ingenious thing. So he decided to counter natural randomness with synthetic randomness. So how did he do that? He divided his field into very small squares, and then he decided with a coin toss for every square whether the square gets a fertilizer or the square does not get the fertilizer. So note here here the the coin toss is very important, because had Fisher done that arbitrarily, he would have been wrong, because his personal biases might have correlated with some unknown confounder. So a coin never lies that way. So if the randomness is done properly and if there is enough squares, it virtually ensures that all the confounders, the sunlight, the water seeping in, the soil, they get divided equally into the control group and the treatment group. So finally, with this ingenious trick, Fisher was able to then measure the yield in the squares with the fertilizer and the squares without the fertilizer. and that is how Fisher was able to calculate the causal impact of the fertilizer on his crops. And that was the birth of modern randomized control trials. It is what essentially you are doing today in the form of A/B testing. Why it is important is because it is the gold standard of causal discovery. So if you ever want to study the effect of one variable on other, the causal effect of one variable on the other, randomized control trials in today's world are the gold standard. So if you cannot run an experiment, that is when you look out at other methods to estimate the causal impact. So, for instance, one example where Fisher himself could not run a control trial was to establish the impact of smoking on cancer. So, because it's unethical to force a bunch of people to smoke and a bunch of people not smoke, so that is why an experiment could not be run there. So, on a lot of social studies today and everywhere, a randomized control trial cannot be run. That is why other methods are sought out for. Luckily, in A/B testing, a randomized control trial can be run very easily. So, moving ahead.
This is Romo Santiago from Experiment Nation. Every week, we share interviews with and conference sessions by our favorite conversion rate optimizers from around the world. So if you like this video, smash that like button and consider subscribing. It helps us a bunch. Now back to the episode.
I would want to address a question first before we move ahead. That okay, so Fisher did invent this method of randomized control trial, but where does statistics come in? Like for all practical purposes, Fisher could have simply taken the yield from the control group and the yield from the treatment group, and then just compared the numbers simply. So suppose the yield from the control group is X and the treatment group is Y, then if Y was greater than X, Fisher could have estimated the causal impact. He could have understood that the yield is increasing, but yet statistics is indispensable. I will take you through a small thought experiment to convince you in what scenarios statistics becomes indispensable for experimentation and when in what scenarios stats would not be needed. So let's imagine that you have to go from point A to point B, and you have two routes to go from point A to point B, which is route 1 and route 2. And I ask you this question, that which route is shorter? So the modern day, so in the modern day, you just flip open your Google Maps, and then you key in the source A and destination B, and then suppose Google Maps shows you 7.6 kilometers on route 1 and 7.8 kilometers in route 2. Now the fundamental here is that no amount of statistics can refute the fact that route 1 is shorter. This is because distances are not random. Essentially, no matter how many times you do this experiment or you test this out, it will always be fixed. And even this 7.6 kilometers, even if it was 7.75 kilometers, then also you can surely say that route 1 is shorter. But suppose I ask you a different question this time. Suppose I ask you that which route is faster. Now the question becomes interesting. So suppose you do the same thing. You open up your phone, you switch on the Google Maps, you key in the source and the destination. And then this time, suppose you see that route 1 is taking 24 minutes and route 2 is taking 25 minutes. How do you decide? Now, because time is random, it might be that there is more traffic on route 2 today, but tomorrow route 2 comes out to be faster than route 1. And in this case, statistics becomes indispensable because you are asking essentially a question about the future, whether this difference of 1 minute between route 1 and route 2 is this significant enough. Had this been 20 minutes and 25 minutes, you would have been sure. You would have been more sure that route 1 is faster. But now, because this difference is so close, you have to ask yourself if this difference is significant enough to stick like this in the future or not. And that precisely why statistics is needed in experimentation. All metrics that you measure, all the data that you measure is random, and hence when you run an experiment, you are sampling from a random variable, and that is why if the difference comes out to be small, which is generally the case. You want to be sure that this difference will stick into the future. So that is why statistics is needed in experimentation. So with this core intuition, let's move forward. Next, I would want to explain you this core concept and the core forces behind statistical significance. So, statistical significance is the p value or the chance to beat baseline or some measure of the percentage that b is better than a or the variation is better than control that you get in experimentation. And in this slide, I'm going to tell you that what are the forces behind the statistical significance. Interestingly, these forces align very well with the intuition, with the regular human intuition. So let's first see this the photo on the left. So the first thing here is the effect size to standard deviation ratio. So if you see that there is a blue signal and there is a red signal, and the blue signal is essentially the variation in this case, the red signal is the control. And there are two cases above and below. In the above case, as you see, in both cases, the mean control value is 10 and the mean variation value is 12. But in the above case, the standard deviation or how much the value fluctuates around its average is 5. So essentially, it's 12 plus minus 5 and 10 plus minus 5. In the case below, this fluctuation is not 5 but 1. So it's 12 plus minus 1 and 10 plus minus 1. So this fluctuation is what we call in statistics as the standard deviation. And it is a crucial parameter of the data itself. So some variables fluctuate much more, some variables fluctuate much less. As you see in this case, in the case above, the effect size to standard deviation ratio is less than 1, since the effect size of 2 is less than the standard deviation of 5. In the case below, the effect size to standard deviation ratio is greater than 1, since the effect size of 2 is greater than the standard deviation of 1. And as you see that even intuitively, you can see that it is much more easier to say in the picture below that the variation is better than control because there is less of an overlap. So that is one part of the intuition. That is two variables that I've talked about yet. Now there is another part that I want to address, which is on the right side. So essentially, when you are measuring a control group and a variation group, or like a control page variant of your website and a variation page variant of your website, then essentially the question that you are asking is not that the samples on control are 95% times worse than the samples on variation, or like the samples on variation are 95% times better than the samples on control. Like, for example, to make the intuition very clear, so suppose you are running a revenue test and multiple people are coming on your website and buying some products, and you are proposing this change on your website, and you ask that if this variation is earning better than control or not. The question that you are asking, and this stands for all significance tests, is not that if the samples on variation are 95% times better than samples on control. That will be too much to ask. You are good to go if on average, so this is the key word here, that on average, the samples of variation, the average of the variation is 95% times better than the average of control. So this is a very crux factor. We don't want 95% of samples to be better than to better in variation. We just want that the average variation value to be 95% times, to have a 95% chance of being better than the average control value. And this leads to an interesting thing. We can measure the standard deviation of the samples, but we cannot measure the standard deviation of the mean. So since we want statistical significance for the mean, we want the standard deviation on the left ratio also of the mean. So what we do is we invoke sampling theory. And sampling theory is very beautiful in its own regard, so I'll quickly explain you. So suppose I've taken this example of a pie, and suppose you are this pi is the entire width of the whole population. So what sampling theory says is that there is a population that can never be entirely collected in a sample. So there'll always be a population and you'll always be taking out a sample from it, and that sample will be a fixed size sample, and that population will have a variance of itself. So if you look at this, that there is this width, the width of this pi is represented representative of the standard deviation. Just a second.
Okay, I found this on the web for is represented the representative of the standard deviation. Just second, check it out.
Sorry for that, my Siri. Yeah. So the idea here is that this the whole width of the pi is essentially the standard deviation of the population in general. So the standard deviation of the samples. And what sampling theory tells us is that there is a sample mean that you can detect from the sample. Also, there is a population mean, which is the true mean of the entire population. And how far the sample mean is from the population mean depends on the size of the sample that you have collected. So from that, they derive out this relationship, and this is a very interesting relationship. It says that the standard deviation of the mean, it can be closely approximated or is equal to the standard deviation of the samples divided by the root of the sample size. So essentially, the larger the sample size that you get, the closer your sample mean gets to the population mean. So the error, this is also called the standard error. So the standard deviation of the mean will always be monotonically decreasing as more and more samples are collected. So with this, let's move forward, and let me show you this. So these are the three forces that determine statistical significance, and this defines most of everything about statistical significance. So if you have a Bayesian system, if you have a frequentist system, if you have a sequential system, or if you have some other system, if whatever be the problem, if you are calculating statistical significance, the whole underlying forces are just these three, and that's effect size, standard deviation, and sample size. This relationship governs the entire statistical significance. If this ratio goes up, your statistical significance increases. If this ratio goes down, your statistical significance decreases. So, and essentially, like you generally do not have the control about for the standard deviation because it's the property of the samples itself. Effect size is generally decided by the kind of improvement that you have made. If you have made some improvement that's significantly a leap over the previous design, the effect size will be large, and hence it'll be have a higher statistical significance. And finally, what you can control is the sample size. So the more the sample sizes you put into a test, the more the statistical significance goes towards the extreme. And this is all that governs statistical significance. So this is the first part of the story, and next I'll tell you the second part of the story, where you'll be able to see that how the whole how the relationship between forces determine the errors. So essentially, this is the second part of the story, and then we'll connect the first part and the second part with the statistical power equation. So the error metrics for modern experimenters, I would want to stress, it's a very interesting topic and a very valuable topic, because statistical significance will always have errors in it. It is something that is random by design, and hence it will always have errors. But errors themselves can be of multiple types. So firstly, let's start with the image on the left and the more popularly known kinds of errors. So there is a false positive and there is a false negative. These are the two dimensions of errors, and they are independent of each other. So let's start by defining both of these. So false positives. Let's start with false positives. How false positives are defined is that if you know that the idea that if the effect size is zero, so if you know that the idea that you are running is not creating an impact, and if so you can call it in other ways. For this slide, if I call something an AA test, I what I'm meaning to say is not an actual AA test where control and variation are the same. What I'm meaning to say is that there is no practical improvement between the control and variation. And when I call something as the A/B test, I am saying that there is an improvement in the underlying metric of control and variation. So, how false positives are defined is that if you are running an AA test, then what is the chance that you get a winner? So, this is the false positive rate. So, if you run 100 AA tests and 5 of them get a winner with your statistical apparatus, we can say that the false positive rate is 5%. The interesting thing about false positive rate is that it is decided by the cutoff value you choose. So suppose that you are essentially looking at a value called chance to beat baseline, the chance that the variation is better than control. Then if you choose to take a decision of deploying at 95%, you are essentially committing to a false positive rate of 5%. If you choose to deploy at a false at a chance to beat baseline of 99%, you are committing to a false positive rate of 1%. So as you see, this is directly under your control. The other thing is a false negative rate. False negative rate is also under your control, but through a very different method. Let's start by defining it. So if you are running an A/B test where there is an actual difference of mean value between variation and control, then what is the chance that the system is not able to detect that difference? That is the false negative rate. So essentially, if you ran an experiment, there was an effect size, but still there is a chance that this effect size does not get detected, and that's the false negative rate. And suppose you ran 100 such experiments, and in only in 80 of those could you actually declare a winner where there was a true winner, then you can say that the false negative rate is 20%. So false negative rates are interesting because they can be controlled by the number of samples you put into the test. And the complementary of false negative rate is statistical power. So if your false negative rate is 20%, then statistical power is 100 minus 20%, which is 80%. And we generally don't talk in terms of false negatives. We talk in terms of the statistical power. And statistical power in experimentation is very much like the power of a thermometer. So if you have a very high power thermometer, then you'll be able to detect very small and nuanced fevers from it as well. If it is a weakly powered thermometer, then only significant temperature changes can be detected from it. So power is like how nuanced of a difference can you find from an instrument. So if you are making a very small change, like Google ran a very famous experiments of 42 shades of blue, it was expected to yield a very small difference in the conversion rate. So they needed a very high power experiment for that. And how do you achieve a high power experiment? You increase the number of sample sizes. So this is something that we'll talk about in the next slide as well. For the time being, I want to discuss something very interesting. These are not the entire kind of error rates. These, what I would say, is the frequentist definition of error rates, the false positive and false negative. They are definitely more powerful. They are definitely more popular. Not powerful. They are definitely more popular. The other one are less popular, but in my opinion, they are what matter more to an experimenter, and I'll explain why. So, False positive rates have a cousin called false discovery rates, and it's very imperative that we understand the nuance difference. So, how we defined false positive rates was that if the experiment that you are running is an AA test, then what is the chance of getting the winner? Now, the false discovery rate is that if you had gotten a winner, what is the chance that it was actually an AA test? And so one is anticipative in nature. The first one is anticipative in nature. It is it is something that assumes the cause beforehand and then tells the probability of the effect. The other is retrospective in nature. So false discovery rates are retrospective in nature. Why? Because they assume the outcome and then tell you the probability of the cause. And this is something that we'll discuss very interestingly in the last slide as well. But the thing is that these might seem correlated, but as it turns out that they can be vastly different because there is one other moving parameter in this whole in false discovery rates. So let's see the example, and I'll explain through this very interesting example. Let's take two cases. In both the cases, we have run 1,000 total tests. In case one, 500 of those 1,000 tests were A tests, and so let's see case one first. So if there are 500 AA tests and 500 AB tests, so let's assume that false negative rates are zero. Only we are looking at the false positive rates. So out of these 500 AA tests, the blue ones here, you'll get a winner in 25 of them because it's a 5% false positive rate. We have maintained a 5% false positive rate. Among the 5% among the 500 AB tests, you'll get all of them as the winner because false negative rate is zero. So in total, you got 525 winners, out of which 25 were bogus. 25 were actually AA tests. So your false discovery rate is 25 by 525 and it's hence 4.7%. Now in case 2, let's look at another extreme case. Suppose 990 of the tests that you ran actually did not create an impact and were actually AA tests. And 10 of the tests that you ran were actually AB tests. And this is something that is more towards the actual scenario, although not extreme, but in general, it is difficult to create an impact in experimentation. So there are always lesser AB tests, more commonly AA tests. So in this case, out of those 990, with a 5% false positive rate, rounding off, you get 50 winners, and you get these 10 AB tests as winners. So in total, you got 60 winners, out of which 50 were bogus. So effectively, we have kept the false positive rate as the same in both situations, but your false discovery rate has gone from 4.7% to 83.3%. So essentially, what I wanted to show here is that false discovery rates do not entirely depend on the instrument itself. It also depends on the number of improvements that you are actually able to make. So if you are making a lot of improvements in your tests, in your experimentation journey, then your false discovery rates will be low. But if most of your ideas are bogus, then your false discovery rates will be very high. You'll be getting lesser winners, and most of those winners will be false. So this is something that I feel that matters more to the modern experimenter than false positive rates. This is still not a very popular concept in the industry right now, in my opinion. So just one last thing that I want to point here is that like false positive rates have a cousin, and I like to call them the Bayesian cousins, the false discovery rates. Similarly, the false negative rates also have a Bayesian cousin. I call them the false miss rates. The chance that if if your test has failed, if your test did not give a winner, what is the chance that there was actually an improvement that it missed out on? So it's very hard to control false discovery rates and false miss rates. Why? Because this prior that I'm calling here, the chance of making an improvement, it's uh, it's not essentially measurable, and it can only be measured from the instrument of experimentation, which is itself. So it's a looped problem that The instrument itself has an error rate, and if this prior is smaller than that error rate, you'll never be able to read into that prior, essentially. So estimating this prior is hard. That is why controlling the false discovery rate and the false miss rate is hard. If this prior is given, or if you can take a good guess on this prior, then it's elementary to just reverse engineer this equation and then calculate the desired false positive and false negative rates that you can then plug into your system. Talking about plugging into the system, now I want to come to what connects both these stories together, and this is, in my opinion, the most interesting thing about experimentation, and this is the supreme power in experimentation. So this is the statistical power equation. So we talked about four things here. We talked about two error rates. Let's leave out the Bayesians for now. We talked about the false positive rate and the statistical power. Naturally, false negative rate and statistical power are the same thing. They are complementary to each other. So referring to one of them suffices. So false positive rate and statistical power are the two error rates. And then there is this MDE to standard deviation ratio. So standard deviation is something that you cannot control. MDE is the minimum detectable effect. So let's spend a minute here. So what is the minimum detectable effect is that suppose you are running an experiment and you say that I want to detect a minimum 2% effect. So this minimum defining is important because if you want to detect an effect smaller than this, it will require a larger sample size. But for this minimum effect size, you can get a maximum sample size for which that can be detected with some accuracy as defined. So that's the minimum detectable effect, and it matters in the ratio of in the ratio with standard deviation. But standard deviation is not movable; it's an environmental parameter. It's an extraneous thing, so that need not be referred explicitly. But this MDE and finally the sample size. So these four things: false positive rates, statistical power, MDE, and sample size. These come beautifully connected into a four-dimensional equation, which is the equation of statistical power. And the beautiful thing about this equation is I'm not going into the details of the equation because it gets too convoluted. But it's very easy to find. All mathematical modules implement this formula. The interesting part about this formula is that you plug in any three of these values and you are able to get the fourth one. So essentially, if you define the false positive rates that you desire, if you define the statistical power that you desire, and the MD that you need, it will tell you the sample size for which you need to run this test so that it is sufficiently powered to detect an effect size of the minimum detectable effect. So if I say that I want a 5% minimum detectable effect, and the conventions, the general statistical conventions for false positive rate is 5%, statistical power is 80%, and suppose it gives me some sample size like 10,000, then how I interpret the sample size is that within 10,000 samples, if there is an effect of minimum 5%, then it will be detected 80% of the times. If there isn't an effect of minimum 5%, then there is a 5% chance that you'll get a false winner. So that's about it. So essentially, that is the equation of statistical power. I personally feel that it is the supreme power with which you can play around with statistical significance. Finally, I would want to move to the last part of our discussion, which is very, very interesting. And I'm trying here to give a very novel perspective on the Bayesian versus frequentist debate. And I have pieced this perspective from various books. One of the books that majorly influenced this perspective is Judea Pearl's The Book of Why. So I would want to answer some questions here and would want to throw the light on the Bayesian and frequentist debate. So let me first start by the upshot. The upshot is in the modern day setting, we have increasingly realized that in the current efforts, Bayesian and frequentist methodologies give the same statistical significance values and up to two decimal places, but that is when you use an uninformed prior. We'll discuss what is an uninformed prior, but practically they do not create a difference. Statistically, the ideologies are worlds apart. Statistically, they are very, very different, and I would want to discuss here how they are different and their own ways to solve the question of statistical significance. So essentially, we talked about the cause and effect thing in the slides on error rates. So let me define here. So there are not one but two kinds of probabilities generally in statistics. So one is the forward probability. So forward probabilities are all probabilities that are anticipative in nature. So that assume a cause and tell the probability of the effect. So like questions like if I'm holding a pair of aces, what is the chance that I win a poker hand? So here I'm assuming the cause, and then I'm trying to detect the effect and tell the probability of the effect. But there are something that is the reverse of this, that if I have won a poker hand, what is the chance that I started with a pair of aces? And that is a question of backward probability. And the tackling of these is very different. Why? Because forward probabilities are much easier to calculate. So essentially, from the cause, you figure out what different scenarios can happen. Out of those scenarios, you only see that what is the effect of which the probability you are trying to tell, and then you can easily do the numerator denominator thing and tell that probability. But it is not that simple for the backward probability. Why? Because multiple causes can lead to the same effect, and those causes can have their own probabilities of happening as well. So a winner and an A/B test can be caused uh, by actually having an improvement or not having an improvement. And now, actually having an improvement and not having an improvement both can have prior probabilities of their own. So that is the difficulty, and that was solved with the Bayes rule. So essentially, in classical probability, we only had the forward probability. It was in the 18th century that Thomas Bayes invented the Bayes rule and gave us a way to calculate backward probabilities. But backward probabilities are also very difficult, but very computationally intensive to calculate. So, in my opinion, it's only in the 21st century, with the invention of computers, that we have now unlocked Bayesian statistics and Bayesian probabilities. Without the existence of computers, it was very, very difficult to calculate these backward probabilities. So let's see their take on the statistical significance question. So the question that statistical significance tries to answer is that is A better than B or not? Now, interestingly, if you think about it, if we talk about in the setting of an experiment, the cause is the underlying effect size. The cause is the underlying improvement, or whether actually variation is better than control or not. That is the cause. The effect is the data that you are observing. So you don't know the cause. You want to identify the cause, if variation is better than control or not. Your question is about the cause. What you are observing is the data that you collect from the experiment. So essentially, the fundamental query of an experiment is backward in nature, and hence it is Bayesian in nature. But it was very hard to calculate the probability of is A better than B or not. So frequentists handled this question with a very interesting hack. The hack was frequentists had to assume a cause, and there could be many causes. That variation could be twice as better than control, variation could be half as better than control, variation could be uh, 5 times as better than control. So which one to choose? So essentially, what frequentists did, that they chose this one hypothesis from which calculating the probability of the effect was easy. And this was the null hypothesis, that the control and variation are the same. If they had to assume that the control and variation are not the same, then that would have been a composite hypothesis. It would break down into many hypotheses of its own. and then you have to choose among those. But this is a pure hypothesis. The null hypothesis is pure. That control and variation do not have a difference, so the effect size is zero. And then they decided that they'll calculate the probability of observing the data that has been observed. So more specifically, the data as extreme as has been observed. So that is how the p-value is defined. So p-value is the chance that you would have observed as extreme the data as was observed in the experiment, assuming that the control and variation did not have a difference. And now the hack that they applied was that the frequentist said that if this p-value, remember, it's not the probability that b is better than a, it is the p-value. If the p-value is very low, then we'll reject the null hypothesis. If the p-value is high enough, then we'll accept the null hypothesis. So, and that's where they put the cutoff. So if p-value is below 0.05, we'll reject the null hypothesis and accept the alternate, that there is a difference. If it's not, then we'll stick to the null hypothesis. And that was the frequentist way to solve this problem, because frequentists did not have a way to calculate the backward probabilities, essentially. Now, how Bayesians solved the problem was very interesting. So they actually tackled these composite hypotheses. So rather than having a null and an alternate hypothesis, they took all the cases and they created a spectrum out of those. But it was and then they calculated, basically not for one case but for all cases, that what is the chance of observing the data that has been observed from different cases. So it comes out into an integral equation, and then you divide by the total probability mass. So if there are these multiple p-values, you sum these up, and then you take the total probability mass and then you place it in the denominator. So you're just applying the Bayes rule, and then you tell what is the chance that the b is greater than a, or b is greater than 3 times a, or b is worse than half times a. So all those questions can be answered once you move to that composite hypothesis scenario. So that was the Bayesian way to answer the things, but Bayesians had a problem. The problem was, how do you define the prior? Like, these different cases, they can have different prior probabilities, they can have different chances of existing, and that is something that cannot be measured. So and without the prior, the Bayes rule does not work. So what Bayesians did here was a very interesting thing, that they use an uninformed prior. They filled a placeholder equation there, they filled a placeholder distribution there that did not have any information of its own, and it properly represented all the information that data represented. So they filled a placeholder. So all modern Bayesian solutions, they use this placeholder prior that does not bias the solution on its own, and it tells you that what is the probability that b is better than a. But interestingly, these forward probabilities and these backward probabilities, in the absence of a proper prior, they are the same. They come out to be the same. They are correlated. It's only the prior that adds extra information and makes the Bayesian probabilities different from the frequentist probabilities. But this prior cannot be easily obtained. So that is the paradox. Now, all modern platforms, they use an uninformed prior, and hence that is why I tell you that the frequentists and Bayesians give the same solution, because the prior is essentially uninformed. If the prior is informed, then it drives the solution towards a more informative answer. And here, what I want to tell you is that the prior that really matters here is the prior of making an improvement. So it's, again, it boils down to the false discovery rate conundrum, that Bayesian statistics, in my opinion, is helpful. Why? Apart from a lot of interpretation related things that now you can do with the Bayesian statistics and a lot of other questions that you can answer, the main reason that Bayesian statistics is helpful is that if you can guess the prior of making an improvement, the chance that you are making an improvement, then you can essentially control the false discovery rate. And that is what matters to the experimenters. And that is why I think Bayesians, that is where I feel Bayesians have the real promise of providing some value. And that is what we are also researching in. And there are no straightforward ways to note the prior. And that is pretty much the Bayesian versus frequentist debate for you. And there are many more angles to it. Uh, Bayesians criticize the frequentists. Why? Because the frequentists do not acknowledge the effect of the priors. The frequentists only look at the probability of the data, whereas the priors do matter. If the prior probability of making an improvement is too low, then the frequentist system with a fixed false positive rate will start to give a lot of false discoveries. Frequentists criticize Bayesians. Why? Because firstly they say if the priors are not obtainable, then why do we have to do something more complex than what is required? And secondly, the frequentists say that even if you have a prior, then it's unfalsifiable. It is not data based. And it is something that you make a guess on, and then it cannot be refuted with data. So the prior always will be there, and it will never be refuted with the data. So that is where the Bayesian versus frequentist debate lies. In summary, for modern experimenters, I would say that at least in the current scenario, you can choose any as long as you confirm that you do not know how to, you do not know your priors, and whatever Bayesian system you are using has uninformed priors. And naturally, I would also want to say here that I have worked with the Bayesian system more. So there would be some developments on the frequentist end that I am not very well versed with. But my preferences for the interpretation, and because the fundamental query of statistical significance is one of backward probability, I personally vouch for Bayesian statistics, although I accept that in the current scenario, there is no difference in the answers they give. So that is my all the ideas that I wanted to discuss. I would like to close with a joke. If at first you don't succeed, try two more times so that your failure is statistically significant. So I'm always eager to talk to all experimenters to address all queries of around statistics and experimentation. I hope you enjoyed my talk. Thank you for your attention and time.
This is Romo Santiago from Experiment Nation. Every week, we share interviews with and conference sessions by our favorite conversion rate optimizers from around the world. So if you like this video, smash that like button and consider subscribing.